Hello, in this lab I analyzed the motion of a spring mass system where the mass swings in an arc while oscillating on the spring. This motion is meant to mimic some of the behavior we see in rope swings. The results of this lab model the energy principle. My results show that the change in energy equals the work done by the surroundings. By choosing the spring, mass, and earth as my system, there is no work done by the surroundings, and my results confirm this as the change in energy is zero. This satisfies the energy principle. Let's look at the video that I analyzed. Using Tracker, I calibrated the length of the stretch spring and aligned the axis so that the pivot was the origin of the axis. The length of the stretch spring was 0.7 meters. Now let's watch the video. Using Tracker, I found the position of the mass at each frame. This gives us the initial mass position and observed position points, which we can later compare to predicted positions from our model. Since it is released from rest, the initial velocity is the vector 0, 0, 0. In order to understand this lab, it is crucial to understand the different principles and concepts used to calculate energy. Using the same spring and mass in a vertically oscillating setting, we determined that the relaxed length and the spring constant of this particular spring. The spring constant is 6.83 newtons per meter. The relaxed length is 0.123 meters. In order to find this stretch, we can subtract the mass position from the spring position, the origin, to get the stretch length, and then we can subtract that from the relaxed length. We then find the unit vector L hat, which we will use later. Now, there are three different types of energy in this system. We need to find the kinetic energy of the spring mass system, the gravitational potential energy, and the spring potential energy. The kinetic energy is 1/2 mass times velocity squared. The gravitational potential energy is mass times gravity times the mass's vertical position, also known as mass times gravity times height. The spring potential energy is the integral of the spring constant times the stretch. We take the integral because the force is changing. Thus, we get 1/2 times the spring constant times the stretch squared. These are represented in Python code here. To update the force of gravity, we use negative mass times gravity. For the spring force, we use the negative spring constant times the stretch times the unit vector in order to make it a vector. The net force is these two added together. We update the velocity by applying Newton's second law. V final equals V initial plus the net force times the time step delta t divided by the mass. The position is updated by the initial position plus the velocity times the time step. Then, using the same equation from before, we update the stretch. Then again, using the same equations, we update the kinetic energy, the gravitational potential energy, and the spring potential energy. By subtracting the final from initial, we can find the change in each of these energies as well. And then we can graph these quantities to observe them as the spring oscillates. Let's try running the program. Here, the x-axis is time, and the y-axis represents energy. The change in kinetic energy is the blue line, the change in spring potential energy is the red line, and the change in gravitational potential energy is the green line. The change in energy of the total system is the yellow line. Now, let's run the program with the intention of comparing the observed motion in Tracker to our model. If we look at the red ball, it represents the observed motion of the mass from Tracker. This graph shows the observed motion versus the predicted motion. As you can see, the model predicts the motion fairly well. A better prediction could have been made by making more careful marks in Tracker. Here, the x-axis represents time, while the y-axis represents the position of the mass. What does it mean? In order to conduct further analysis, I imported the position points and the time points from Tracker into Excel, and then graphed the time versus x position and the time versus y position. First, we need to see whether or not the energy principle is satisfied. In this system, the energy principle is satisfied. It states that the change in energy of our system is equal to the work done by our surroundings. Since we choose the spring, mass, and earth as our system, there is no work done by our surroundings, and the change in energy is zero. As shown by the yellow line in our model, this is true and the energy principle is satisfied. Second, let's compare the two separate estimates of oscillation periods. Using the data from Tracker, I graphed the two estimates of oscillation periods. Since x is based on pendulum motion and y is based on a spring motion, they have different periods. Using these graphs of motion versus time, I found the time it took to complete 5x and 5y periods. Then, by dividing by 5, I estimate each period. The period of x was close to 1.63 seconds, and the period of y was close to 1.52 seconds. The y oscillation is based on mass and the spring constant, as shown by the period of a spring equation, while the x oscillation is based on the length of the spring and gravity, as shown by the period of a pendulum equation. In conclusion, the computational model predicted the motion of our observed mass quite accurately, and it showed that the energy principle is satisfied since the change in energy is zero and no work is done by the surroundings.